Cohesion is basically about how much the things inside a module actually belong together. When a module has good cohesion, all of its parts feel like they're part of the same job. When it has bad cohesion, the module feels like a random collection of tasks that don't really match. The weakest kind is coincidental cohesion. This is when a module is just a bucket of unrelated stuff. Maybe someone didn't know where to put some functions, so they shoved them all into one file. Nothing inside has a real connection. It's like opening a drawer and finding batteries, socks, a spoon, and a phone charger all together. It works, technically, but it makes everything harder to understand and harder to maintain. Next is logical cohesion. This is a little better, but still not great. Here, the tasks inside the module fall under one broad idea, but they're still doing completely different things. Imagine a module that says input operations, but inside it has functions for handling mouse clicks, keyboard input, voice commands, all unrelated except for the label. It's like saying, these things all involve input, so let's stuff them together. It's more organized than the first type, but the module still doesn't feel focused. Then comes temporal cohesion. This happens when tasks are grouped together because they occur at the same time, not because they're related in purpose. A good example is startup code, loading configuration, opening a log file, checking memory, initializing hardware. They all happen during startup, so they get thrown together. They don't really share a functional goal, they just share timing. It's better structured, but still not truly unified. After that, there's procedural cohesion. This is when tasks go together because they're part of a sequence. You do step 1, then step 2, then step 3. They form a flow. But even though the steps follow each other, they might still handle different responsibilities. Think of a function that validates input, then logs the event, then stores data, all in a single run. These tasks happen in order, so they fit procedurally, but they still mix different concerns. Better than the earlier types, but still not ideal. A strong step forward is communicational cohesion. This is when all the tasks in the module work with the same data. Maybe everything in the module manipulates a specific customer record or reads from a specific file. Even if the actions differ, the focus on a single data source ties everything together. This kind of cohesion feels more natural because you can tell what the module is centered around. It's easier to test and easier to follow because everything revolves around one thing. And at the top is functional cohesion, the best kind. This is when everything in the module supports one clear purpose. Every function, every line of code contributes to one well-defined job. This makes a module incredibly easy to understand. You open it and immediately know what it does. It's also easier to test because it has one predictable behavior, and easier to change because everything inside points toward the same goal. This is the type of cohesion good software aims for. When you compare all the types, you can see a pattern. As cohesion gets stronger, the module becomes more focused, cleaner, and easier to maintain. As cohesion gets weaker, the module becomes more scattered and confusing. Functional cohesion is the best because it gives each module a single purpose. Coincidental cohesion is the worst because it mixes unrelated logic and makes everything harder. High cohesion happens when modules are designed around one responsibility. Low cohesion happens when modules take on too many tasks or act as dumping grounds for unrelated code. Improving cohesion often means splitting big modules into smaller, more focused ones and making sure each one handles exactly one area of responsibility. When cohesion is high, the software feels organized and dependable. When cohesion is low, the system becomes chaotic and full of hidden problems. High cohesion is one of the main signs of good design. Coupling is all about how much one module depends on another. If two modules are tightly connected and can't really work without each other, that's high coupling. If they can work mostly on their own and only share what they absolutely need, that's low coupling. Low coupling is what you want because it makes your system easier to change, easier to test, and easier to understand. The worst kind is content coupling. This is when one module directly reaches into another module's internal stuff, like private variables or hidden logic. It's like opening someone else's else's drawer and rearranging their things. If the inside of that module changes, everything that touched it breaks. Content coupling makes the whole system fragile because one small change can cause a chain reaction of failures. Then there's common coupling. This happens when modules share the same global variables or global state. Imagine a bunch of people all sharing one wallet. If one person takes money out, everyone else is affected. That's what common coupling feels like. Any module can change the global value, and the others have to deal with the consequences. It creates unpredictable behavior and makes testing really annoying because you constantly need to reset the global state. Next is external coupling. This is when modules depend on the same external things, like a file format, a communication protocol, or a specific hardware interface. The modules might not depend on each other directly, but they're tied together through this outside system. If the file format changes or the hardware behaves differently, anything relying on it breaks at the same time. It's not the worst kind of coupling, but it can still cause headaches if the external system isn't stable. Another one is control coupling. This happens when one module tells another module how to do its job, usually by sending flags or special codes, like do this mode, run that path, or behave like this. It means the first module needs to know too much about how the second module works internally. It's like giving someone directions, but also telling them exactly which turns they must take, instead of just letting them choose their own route. When control information changes, everything depending on it has to change too. Then there's stamp coupling, also called data structure coupling. Here, modules share an entire data structure even though they only need a small part of it. It's like giving someone your entire backpack when all they wanted was a pencil. If the shape of that backpack changes, maybe new pockets get added or old ones get removed, every module that receives the whole structure feels the impact. It's better than the types above, but still not ideal because the modules depend on a bigger structure than necessary. A much better kind is data coupling. This is what most developers aim for. In data coupling, modules only share the exact data they need, nothing more. There are no global variables, no big complex structures, no special mode flags, just clean, simple inputs and outputs. When you have data coupling, modules are easier to reuse, easier to test, and far safer to change because the dependencies are small and clear. And at the far end, there's no coupling, which means two modules don't interact at all. They're completely separate. This is perfect independence, but obviously not every part of a system can operate without talking to others. Still, it's useful as a concept because it shows what total separation looks like. When you compare all these types, you can see a clear trend. The more a module depends on another module's internal details or global state, the more fragile the system becomes. As the coupling becomes weaker, meaning the modules depend on less and share only what they absolutely need, the system becomes more flexible and stable. The best realistic form is data coupling because it gives you communication without unnecessary dependency. The worst is content coupling because it creates a brittle system where everything breaks if anything changes. Coupling becomes a problem when modules reach into places they shouldn't, share too much data, rely on global variables, or tell each other how to behave instead of just exchanging the information needed to do their jobs. To avoid high coupling, you keep modules focused, share only essential data, avoid globals, and give each module clear, simple interfaces. When coupling is low, the software feels modular and easy to work with. When coupling is high, everything feels tangled and risky to change. Low coupling is one of the biggest signs of well-designed software. Coupling and cohesion fit together like two sides of the same idea. Cohesion is about how focused the inside of a module is. Coupling is about how much a module leans on other modules. Good software aims for high cohesion on the inside and low coupling between the modules. When you get those two right, your system feels organized, easy to change, and much simpler to understand. In simple terms, strong cohesion means everything inside a module belongs together and works toward one clear purpose. Weak cohesion means the module is doing too many unrelated things, so it feels messy and scattered. With coupling, it's the opposite. You want very little of it. Low coupling means modules don't depend heavily on each other. High coupling means changing one module forces you to change others too, like a chain reaction you never wanted. Bad cohesion happens when a module becomes becomes a dumping ground for random tasks. This usually happens because someone is in a hurry, or the project grows without structure, or people keep adding new features without thinking about where they truly belong. Over time, the module loses its identity and becomes a catch-all file. You can avoid bad cohesion by giving every module a single, clear responsibility. Whenever a module starts doing too much, that's a sign to split it up. Keep each piece focused, and don't mix unrelated logic together just because it feels convenient in the moment. Bad coupling happens when modules start depending on things they shouldn't depend on. Maybe they reach into each other's internal data, maybe they rely on global variables, or maybe they pass around giant data structures instead of just what they need. Sometimes it happens because the quick solution is to tie modules together instead of designing a clean boundary. Other times it happens because a new developer doesn't understand the architecture and accidentally creates dependencies that weren't meant to exist. You avoid bad coupling by keeping interfaces clean and simple, sharing only essential data, and never exposing internal details. Avoid global state unless you absolutely need it, and avoid passing control flags or huge objects when a small piece of information is enough. Both problems also appear when teams rush, when requirements change too quickly, or when nobody is watching the overall structure. A system slowly becomes tangled and unfocused without anyone noticing. The good news is that avoiding these problems usually comes down to a few habits. Keep modules small and focused so cohesion stays high. Keep communication between modules simple so coupling stays low. Don't let unrelated logic sneak into the same place, and don't let modules depend on more than they need. Think of each module like a worker with a clear job. It should know exactly what it does and should only get the information necessary to do that job. When cohesion stays strong and coupling stays low, everything becomes easier. Testing, fixing bugs, adding new features, and even understanding the whole system. The code feels clean instead of tangled, and the structure feels intentional instead of accidental.